The largest structures in our universe are vast, empty spaces. Cosmic voids stretch for hundreds of millions of light years, and their profound emptiness challenges everything we think we know about reality. By the end of this journey, you will understand why these great nothings are the key to unlocking the universe's deepest mysteries. We will explore how empty space can push our galaxy, and what these voids reveal about the dark energy tearing the cosmos apart. What does true emptiness feel like on a cosmic scale? A cosmic void is far more than just an empty patch of darkness. Think of the universe as a colossal, three-dimensional web, with brilliant galaxies strung along its glowing filaments and packed into dense, shining knots. The voids are the immense, shadowy spaces in between. They are the universe's negative space, the vast, silent rooms that give the grand cosmic mansion its structure and scale. Within these regions, the density of galaxies plummets to almost nothing. A typical void can span over 100 million light-years, yet it might contain only a few dozen lonely galaxies, each an isolated island in an ocean of near-nothingness. But this emptiness is a relative term. A cosmic void is not a perfect vacuum. It is filled with a ghostly, invisible scaffolding of dark matter and a whisper-thin mist of hydrogen gas, so diffuse it is almost undetectable. This foundational truth that the emptiest places in the cosmos are still filled with unseen substance is what makes them so pivotal. To truly comprehend their role, we must first attempt to grasp a scale that defies all human intuition. One of the most startling examples of this cosmic emptiness is a place called the Boote's Void. Its discovery in the 1980s sent a ripple of awe through the astronomy community. This is not a small pocket of space. It is a spherical region of the universe roughly 330 million light-years across. To understand what that number truly means, picture our own local neighborhood of galaxies, the local group, which includes Andromeda and the Milky Way. This entire collection, spanning millions of light-years itself, would be a mere speck if placed inside the Boote's Void, utterly lost in the expanse. The scale is so profound it reshapes history. If our solar system had somehow formed at the very heart of this void, our telescopes would have seen nothing but black, empty space in every direction. The first evidence of other galaxies beyond our own would not have appeared in our skies until the 1960s. We would have spent centuries believing our Milky Way was the entire universe, a single, lonely island in an infinite, starless sea. How does the universe create a nothingness so vast it could hide the rest of creation from us? The existence of such a void forces us to confront the very mechanisms that built the cosmos. The seeds of these great voids were sown in the universe's very first moments. In the searing heat of the Big Bang, the infant cosmos was not perfectly smooth. Tiny, random quantum ripples, fluctuations in density smaller than a single atom, were imprinted upon the fabric of reality. For billions of years, gravity acted as the universe's great sculptor, working on these tiny imperfections. Regions that started with just a fraction more density than their surroundings began to pull matter in, growing ever denser, but the opposite was also true. Those pockets that began with even a minuscule deficit of matter faced a gravitational disadvantage. Think of it like a gentle slope in an immense cosmic landscape. Matter naturally began to slide away from these underdense regions, flowing downhill towards the denser hills and mountains. Over cosmic time, this gentle drainage became a full-scale evacuation. The slightly emptier regions expanded faster than the universe itself, their boundaries pushed outward by the relentless pull of the surrounding denser structures. What began as a microscopic dimple in the early universe stretched into a cavernous void, hundreds of millions of light-years wide. This is the dual nature of cosmic evolution, a grand tug of war where gravity builds up the shining filaments of the cosmic web by simultaneously carving out the profound darkness between them. To see this invisible architecture for ourselves, we need a way to map the emptiness. Astronomers face a unique challenge, tasked with mapping immense structures defined by their absence. They cannot simply point a telescope at a dark patch of sky and see a void. Instead, they must chart the universe in 3 dimensions, meticulously plotting the positions of millions of galaxies to reveal the great empty spaces between them. This cosmic cartography is the work of massive redshift surveys like the monumental Sloan Digital Sky Survey. This project methodically scans the heavens, collecting light from countless galaxies to measure their redshift. A galaxy's redshift tells us how much the universe has stretched since that light began its journey, effectively giving us its distance. By combining this distance with its position on the sky, astronomers can build a 3-dimensional map of the cosmic web. The voids emerge not as objects seen, but as cavernous gaps in the data, vast bubbles where the pinpricks of galaxies almost completely vanish. These maps are the blueprints of nothingness, revealing the true architecture of our universe. But the story does not end with a static map. The galaxies that do linger on the edges of these voids are in motion, and their movements tell a hidden tale. These are called peculiar velocities, motions that deviate from the smooth expansion of the universe. Galaxies near a void often show a subtle but measurable flow, sliding ever so slightly down the gravitational slope away from the emptiness. This movement is a crucial clue. It confirms that even these near-empty regions possess a gravitational signature, shaped by their unseen dark matter content and the push of dark energy from within. The kinematics of these boundary galaxies act as a cosmic probe, allowing scientists to weigh the void itself and understand the forces sculpting it from the inside out. This technical insight bridges our theories with hard evidence, transforming the void from a theoretical concept into a dynamic, measurable component of the cosmos. It forces us to ask, if we could step inside one of these great voids, what would we actually find floating in the profound darkness? The emptiness of a cosmic void is a profound illusion. Step inside one of these vast regions, and you would not find a perfect vacuum. Instead, you drift through an unseen architecture of dark matter, a ghostly framework that dictates the gravitational landscape of the entire cosmos. This invisible scaffold is what gives the void its shape, its sheer gravitational absence pulling the surrounding cosmic web into being. But there is also ordinary matter here, transformed into an almost mythical state. A whisper-thin, superheated gas known as the warm-hot intergalactic medium, or WIM, permeates the darkness. This plasma is so incredibly diffuse that a single coffee mug full of it might contain just a single atom, yet it is so hot it glows with the energy of millions of degrees. This WIM is believed to hold a significant portion of all the normal atoms in the universe, a hidden ocean of matter that has evaded detection for decades, missing from our cosmic inventories. And then there are the rare inhabitants, the void galaxies. These are the lonely outposts of the cosmic frontier. A handful of galaxies, perhaps just a few dozen, might be scattered across a volume of space that could comfortably contain thousands. Isolated from the gravitational turmoil and violent collisions that shape galaxies in crowded clusters, these void galaxies often evolve in quiet solitude. They can be strange, pristine relics, sometimes lagging in their development and retaining more of their primordial gas, offering us a unique window into a more gentle, unperturbed path of galactic life. Far from being barren deserts, cosmic voids are dynamic environments, each with its own complex ecosystem of dark matter, hot gas, and rare, isolated worlds. This realization that nothing is truly empty forces a pivotal question. What invisible force is actively stretching these voids into even greater expanses? This relentless growth of cosmic voids points to a force far more mysterious than gravity. The same dark energy that drives the universe's accelerated expansion is actively inflating these empty regions, stretching them into even vaster and emptier bubbles over time. While gravity pulls matter together to form the dense knots and filaments of the cosmic web, dark energy exerts a kind of negative pressure, pushing space itself apart from within. Nowhere is this push more effective than inside a void, where the gravitational pull from matter is at its absolute weakest. With little to resist it, dark energy dominates, causing the void to expand faster than the universe as a whole. It is a self-reinforcing cycle, a cosmic feedback loop where emptiness begets even greater emptiness. This makes voids the most sensitive instruments we have for measuring the strength and nature of dark energy itself. Cosmologists can observe how quickly a void grows by tracking the motions of the few galaxies on its fringes over billions of years. The rate of this expansion provides a direct, independent measurement of dark energy's influence, a crucial check on findings from distant supernovae. In this way, these great nothings are transformed into active laboratories, giant cosmic petri dishes where we can watch the fundamental forces of the universe play out on the grandest of scales. They are not passive holes in the cosmos, but dynamic entities whose very evolution is dictated by its most elusive component. Drifting in the profound emptiness of a void, a single galaxy tells a story of solitude. These isolated outposts, known as void galaxies, live a life of quiet isolation, cut off from the bustling galactic metropolises that define the cosmic web. Their existence is not one of frantic collisions or dramatic gravitational encounters, but of slow, gentle evolution. In the dense urban centers of galaxy clusters, galaxies are constantly jostled and merged, their gas stripped away, their stars reshuffled in violent events that rapidly age them. But a void galaxy is a cosmic hermit. It holds onto its primordial gas, the raw fuel for star formation, for billions of years longer than its city-dwelling cousins. This results in a galaxy that is, in many ways, a living fossil. It often has a higher fraction of gas, lower amounts of heavy elements forged in stellar explosions, and a more tranquil, ongoing rhythm of new star birth. It resembles the galaxies that populated the young universe, offering us a pristine window into a more gentle, undisturbed path of galactic life. This stark environmental contrast is a fundamental rule of cosmic evolution. A galaxy's fate, its structure, and its very identity are not determined solely by its internal laws, but by its cosmic zip code. The quiet, isolated existence of a void galaxy stands in perfect opposition to the chaotic, violent life found just a short cosmic distance away. This stark division between the quiet void and the crowded cluster defines the very extremes of cosmic existence. On one end of the spectrum lies the galaxy cluster, a roaring metropolis of unimaginable density. Hundreds, even thousands of galaxies are packed into a region of space that a cosmic void would leave almost entirely empty. Here, gravity is an unforgiving tyrant. Galaxies do not simply drift past one another, they collide, merge, and are torn apart in a relentless gravitational dance. Their orbits are twisted and accelerated to incredible speeds, all held together by the immense, invisible fist of dark matter that forms the cluster's true backbone. The space between these galaxies is not empty at all, but filled with a searing plasma, a gas so hot it glows in X-rays and contains more mass than all the cluster's stars combined. This is a violent, chaotic environment where galaxies are rapidly stripped of their gas, the raw material for new stars, and transformed into red, dead relics. It is a cosmic pressure cooker forging galaxies through fire and collision. Now travel to the opposite extreme, into the heart of a cosmic void. The roar of the cluster fades into an almost deafening silence. The frantic gravitational shoving match is replaced by a gentle, persistent expansion. The searing intergalactic gas cools into the thin, elusive mist of the warm, hot intergalactic medium. The few galaxies here are not accelerated to high speeds by a dominating gravitational field. Instead, they drift with peculiar motions, subtly sliding down the gentle gravitational slopes away from the emptiness. Their evolution is not dictated by violent encounters, but by their own slow internal clocks. This is the cosmic frontier, a place of isolation and tranquility. Yet these two extremes, the dense cluster and the expansive void, are two sides of the same coin. Both are sculpted by the same underlying cosmic blueprint, the dark matter scaffold that dictates where matter gathers and where it flees. The cluster marks a peak in the universe's density field, a towering mountain of matter. The void is its corresponding valley, a vast basin of scarcity. One cannot exist without the other, for the very forces that pile matter into brilliant knots simultaneously excavate the dark, empty spaces between them. By studying this duality, we trace the invisible hand of dark matter, understanding how its subtle initial fluctuations were amplified over billions of years to create the full, breathtaking spectrum of our universe's architecture. This gravitational duality between the void and the cluster extends to the very way they bend light. We are familiar with the dramatic arcs and rings created when a massive galaxy cluster acts as a cosmic telescope, warping the spacetime around it so severely that it magnifies and distorts the light from galaxies far behind it. This is strong gravitational lensing, the universe's most spectacular optical effect. But what happens when light travels through a region of profound emptiness? A cosmic void also possesses a gravitational footprint, but it is a negative one. Instead of pulling spacetime into a deep well that concentrates light, the void's relative lack of mass creates a shallow, broad hill. As light from the distant cosmic microwave background, the afterglow of the Big Bang, passes through this under-dense region, it experiences something counterintuitive. It is not focused, but very subtly defocused. The light rays diverge from one another as they cross this gravitational hill, resulting in a minute but measurable cooling of the light's temperature as it reaches our telescopes. This subtle imprint is known as the integrated Sachs-Wolfe effect. It is the ghostly signature of a void's gravity, or rather, its lack thereof, etched directly onto the oldest light in the universe. Detecting this requires comparing the locations of known voids with tiny temperature fluctuations in the cosmic microwave background, a painstaking process that confirms these empty regions are actively shaping the fabric of reality. This faint cooling is more than just a curiosity. It is a direct probe of the universe's expansion history and the nature of dark energy. For this effect to be detectable, the universe's expansion must be influencing the depth of these gravitational hills over time. As dark energy accelerates the cosmos, the gravitational potential of a void evolves, leaving its specific mark on the passing radiation. By measuring this imprint, cosmologists can test the very models of dark energy itself, using the great cosmic nothings as a precise instrument to weigh the force that dominates our universe's fate. The void's subtle warping of spacetime proves that even absolute emptiness leaves an indelible mark on the cosmos. The ghostly imprint on the cosmic microwave background is not the only fossil these voids preserve. Their very size and distribution carry the echo of the universe's first sound. In the earliest moments, the cosmos was a searing, opaque fluid of particles and light, a churning primordial plasma. Within this dense medium, gravity tried to pull matter inward, while the intense radiation pressure of the trapped light pushed it back out. This titanic struggle set the entire universe ringing, creating colossal sound waves that raced outward at over half the speed of light. These are the Baryon acoustic oscillations. For hundreds of thousands of years, these pressure waves surged through the infant cosmos until a pivotal moment. The universe cooled enough for atoms to form, allowing light to travel freely in what we call recombination. In that instant, the waves froze in place, their progress suddenly halted. They left behind a permanent, spherical imprint in the distribution of matter, a subtle preference for galaxies to be separated by a specific distance, a cosmic standard ruler etched into the fabric of space. This preferred scale is about 500 million light-years, but here is the crucial part. It is not just a ruler for where matter is, it is also a ruler for where matter is not. The cosmic voids, these vast empty bubbles, also exhibit this characteristic scale. Their diameters are not random, they too cluster around this same 500 million light-year measurement, a fossilized echo of that primordial sound. This gives cosmologists an incredibly powerful tool. By measuring the apparent size of these voids at different distances, and therefore at different epochs in the universe's history, they can chart how space itself has stretched over billions of years. It is like having a ruler that grows with the universe, allowing us to measure the expansion rate with remarkable precision. The voids, in their profound emptiness, have preserved the universe's first cry, turning it into one of our most reliable guides to the past and future of the cosmos. Our own galaxy is not a stationary island, but a ship sailing through the cosmic sea. For decades, astronomers have tracked this motion, a 600-kilometer-per-second journey towards a mysterious, hidden concentration of mass they call the Great Attractor. But the full story of our voyage is more complex, for we are not only being pulled, we are also being pushed. The other half of this cosmic equation is a profound emptiness known as the dipole repeller. This is a vast cosmic void, a region of such staggering scarcity that its gravitational influence acts like a repulsive force. Just as a ball rolls away from the top of a hill and into a valley, our local group of galaxies is sliding away from this immense underdense region. The Great Attractor pulls us in one direction while the dipole repeller pushes us from the other. This reveals a fundamental cosmic truth. On the largest scales, motion is dictated as much by what is missing as by what is present. It is the gravitational landscape of the entire universe that sets objects in motion, with the towering mountains of dense superclusters pulling matter in, and the vast valleys of the voids pushing it away. Our journey is a response to this full topography, a balance between the push of nothing and the pull of everything. This understanding transforms our view of cosmic flow from a simple tug of war into a complex migration across a terrain sculpted by both presence and absence. Our place in the cosmos is defined not just by the brilliant structures we can see, but by the silent, invisible voids we flee. To see this cosmic architecture form from scratch, scientists run the universe in reverse inside a supercomputer. They begin with a near-perfectly smooth distribution of dark matter particles, each one representing a vast clump of unseen mass, all governed by the simple, relentless pull of gravity. With the press of a button, the simulation begins, fast-forwarding through billions of years of cosmic evolution in a matter of hours. This is the power of an n-body simulation. The term n-body sounds technical, but it simply describes a system that calculates how every single particle gravitationally influences every other particle, a mind-boggling number of calculations that only the most powerful computers can handle. As the simulation runs, those tiny, initial ripples from the Big Bang begin to amplify. Gravity works its magic, pulling particles together into faint tendrils, then robust filaments, and finally, into dense, glittering knots where virtual galaxies would eventually form. And just as predicted, the voids emerge naturally in the spaces between. They are not programmed into the simulation. They are an inevitable outcome, the negative space that must appear as matter coalesces elsewhere. Watching a simulation unfold is like watching a time lapse of a growing crystal, where the empty spaces are just as fundamental to the final structure as the crystal itself. We see the Boote's void and its countless cousins born from pure mathematics and the law of gravity, a powerful confirmation that our basic understanding of cosmic structure formation is correct. But these virtual universes are far more than just pretty animations. They are precise laboratories. Cosmologists can run experiments inside them that are impossible in the real world. They can tweak the laws of physics, for instance, altering the strength of gravity on large scales or changing the properties of dark matter. Then they watch how the voids respond. Do they grow too quickly? Are they the wrong shape or size? By comparing the properties of voids in the simulation to the voids we meticulously map in our own universe, we conduct a powerful test. If the simulated voids match the real ones, it suggests our theories are on the right track. If they diverge, it is a clear sign that something is missing from our model, perhaps a new property of dark energy or a flaw in our understanding of gravity itself. In this way, the great cosmic nothings become a rigorous benchmark, a cosmic scale against which we weigh our most fundamental theories of reality. Einstein's theory of gravity, general relativity, has passed every test thrown at it for over a century. But these tests have largely occurred in places full of matter, like our solar system or near massive stars. Cosmic voids present a radically different environment, a laboratory of near-nothingness where the rules might be different. Some physicists propose that our theory of gravity, while incredibly successful, might need adjustment on the largest cosmic scales. These modified gravity theories often predict that the growth of cosmic structures, particularly the expansion of voids, should proceed at a different rate than general relativity allows. In the dense heart of a galaxy cluster, gravity's pull is overwhelming, masking any subtle alternative effects. But inside a void, where gravity is at its weakest and dark energy's push is strongest, any slight deviation from Einstein's predictions would be magnified and become visible. It is in these quiet, empty places that the universe's most fundamental force might finally reveal a crack in its armor. How do we look for this crack? The key lies in the subtle geometry and dynamics of the voids themselves. General relativity makes specific forecasts about how a void should grow over time, and crucially, how its shape should evolve under the influence of both its own weak gravity and the relentless push of dark energy. Some alternative theories suggest that voids should become more stretched and elongated, or that their walls should collapse at a different rate. By mapping millions of voids and measuring their shapes and the peculiar velocities of galaxies on their boundaries with exquisite precision, astronomers can perform a direct test. They compare the real, observed void to the virtual one predicted by different gravity models running in supercomputer simulations. Does the void match the Einsteinian prediction, or does it align better with a modified theory? Each precisely mapped void acts like a vote, and so far, the consensus is that Einstein's theory continues to hold sway, even in the most extreme emptiness. The voids have not yet broken relativity, but they have placed it in a tighter and tighter box, ruling out many of its potential competitors. This rigorous testing transforms the great cosmic nothings into our most stringent referees, ensuring that our understanding of gravity remains solid, all the way from the crowded planets to the vast, empty expanses between the galaxies. This hierarchy of cosmic emptiness stretches from the smallest pockets to the largest structures imaginable. Even within the dense, glowing filaments of the cosmic web, you can find tiny voids, often called mini-voids. Picture a vast mountain range where the grand peaks are connected by ridges and valleys. A mini-void is like a small, sheltered hollow nestled high on one of those ridges, a pocket of relative emptiness within an otherwise crowded structure. These small voids might span only 10 or 20 million light-years, a mere pocket of quiet in the cosmic metropolis. But then you have the supervoids, the true titans of nothingness. These are the voids we have been discussing, like the Boote's void, regions that can stretch for hundreds of millions of light-years. They are not simple spheres but complex, amoeba-like volumes, often interconnected in a vast, spongy network of emptiness. This entire spectrum, from the smallest mini-void to the largest supervoid, is not random. It is a direct reflection of the universe's initial conditions. The quantum ripples that seeded all structure varied in size and amplitude. Some fluctuations were small, creating tiny dimples of underdensity. Others were immense, laying the groundwork for future caverns of staggering scale. Over billions of years, gravity amplified them all in unison. The small dimples grew into mini-voids, while the largest depressions catastrophically drained of matter, ballooning into the supervoids we observe today. This multi-scale hierarchy is absolutely essential for a complete model of the cosmos. It demonstrates that emptiness possesses its own intricate architecture, a nested system of absences that mirrors the complex hierarchy of the galaxies themselves. To truly understand the cosmic web, you must account for every scale of its structure, from the most brilliant cluster of galaxies to the most profound and layered depths of its emptiness. One of the most tantalizing puzzles written on the ancient light of the cosmos is a place known as the CMB cold spot. In the all-sky map of the cosmic microwave background, this region stands out as a profound and unexpected chill, a vast circular patch of sky that is significantly colder than the average. Its existence is a genuine anomaly, a feature so large and so cold that it challenges our standard models of the universe. What could possibly cast such a giant, cold shadow on the very first light of creation? The leading suspect is a cosmic void of almost unimaginable scale. The theory is a direct application of the integrated Sachs-Wolfe effect. If a truly immense supervoid, a bubble of staggering emptiness hundreds of millions of light-years across, sits between us and the cold spot, its gravitational hill would cause the CMB photons to lose energy as they climb out, cooling the light we receive. It is a perfect, elegant explanation. The hunt was on to find this phantom void. Astronomers scanned the suspected region, painstakingly mapping the three-dimensional distribution of galaxies. And they found something, a large underdense region, a supervoid indeed sitting in the foreground of the cold spot. But here is where the mystery deepens. The void they discovered, while enormous, appears to be just a bit too small and not quite empty enough to account for the entire temperature drop we observe. The numbers do not fully add up. This leaves us with a fascinating dilemma. Is our understanding of how voids interact with light incomplete? Could there be an even larger, more diffuse void that our current galaxy surveys are simply not sensitive enough to detect, its faint outline still hidden in the darkness? Or does the cold spot point to something even more exotic, a remnant of a cosmic collision with another universe, a flaw in the very fabric of spacetime from the moment of inflation. The cold spot remains an open question, a beautiful and frustrating clue. It demonstrates with stunning clarity that these great cosmic nothings are not just passive holes, but active players in the deepest cosmological mysteries we can conceive. The ultimate destiny of our universe may be written not in the stars, but in the voids. As dark energy continues its relentless work, the cosmic web we see today will not last. The delicate filaments of galaxies, the brilliant knots of clusters, all of this intricate structure is temporary. The true, final architecture of the cosmos will be one of overwhelming emptiness. Voids will not merely persist, they will become the universe's defining characteristic. They are growing even now, expanding faster than the universe itself, and they are beginning to merge. Like soap bubbles coalescing into a single, gigantic cavity, adjacent voids will eventually meet, their walls dissolving. The thin filaments of the cosmic web that separate them will be stretched to their breaking point, thinning out until they finally snap. When this happens, any galaxy not already locked into a massive, gravitationally bound cluster will find itself completely isolated. It will be an island universe cut off from all others, adrift in an ever-darkening sea of nothingness. This is the future that dark energy dictates, a future where the great voids are the only things that truly grow. The universe's expansion will accelerate to such a degree that the light from any galaxy outside our own local, bound group will be stretched beyond detection, its photons losing all energy as they fight against the inflating space between us. The observable universe will shrink to a tiny, lonely pocket, while beyond our walls, the true cosmos becomes an incomprehensible expanse of pure, merging void. This is the heat death or the big freeze. It is not a dramatic explosion or a violent collapse, but a slow, quiet fading. The last stars will burn out, and the galactic engines of creation will fall silent, leaving behind a cosmos that is cold, dark, and almost perfectly uniform. In that distant epoch, the voids will have won. Their profound emptiness will be all that remains. This cosmic prevalence of emptiness forces a profound shift in perspective. For centuries, humanity placed itself at the center of everything, but the voids tell a different story. They reveal that our home, a vibrant planet orbiting a stable star within a bustling galaxy, is not the cosmic standard. It is the spectacular exception, the shining filaments of the cosmic web where galaxies gather and stars ignite, are the rare, glittering islands. The true nature of the universe is one of vast, quiet, and overwhelming nothingness. Our entire existence plays out in a privileged enclave, a tiny neighborhood of density in an ocean of absence. This realization can feel deeply unsettling, a recipe for existential dread. Yet, it can also be reframed into something astonishingly beautiful. The very fact that we are here to observe this emptiness, to map these voids and ponder their meaning, is itself a miracle. We are not just distant observers of this cosmic architecture, we are a product of its most unusual and fertile corners. Our ability to look out into the great dark and understand it transforms our place from one of insignificance to one of rare cosmic significance. We are the universe becoming self-aware, a fleeting moment of concentrated consciousness in an expanse that is mostly unconscious and empty. This challenges the very core of an anthropocentric view, the idea that the cosmos was made for us. Instead, we were made by the cosmos, a fortunate and intricate accident within its specific, lopsided conditions. The voids do not make our lives smaller. They make the fact of our existence infinitely more precious. In the grand, silent narrative of the universe, our chapter is brief, but it is one of the very few that is actually being read. The silent expansion of these voids is about to be captured in exquisite detail. A new era of cosmic cartography is dawning, driven by telescopes of almost unimaginable power. The Euclid Space Telescope, now on its mission, is designed to survey the sky with a razor-sharp gaze, mapping the three-dimensional positions of billions of galaxies across 10 billion years of cosmic history. Its primary goal is to measure the subtle distortions in galaxy shapes caused by dark matter, but it will also produce the most detailed chart of the cosmic web ever created. Every filament and, crucially, every void will be pinpointed with stunning accuracy. This is not a static map, it is a cosmic time lapse in the making. By looking deeper into space, and therefore further back in time, Euclid will allow us to see voids at different stages of their lives, from their infancy as small under-densities to their mature, cavernous forms. We will watch them grow, merge, and reshape the universe in real time across billions of years. This evolution is the key to unlocking the precise properties of dark energy. How quickly do voids inflate? How does their growth rate change over the history of the universe? Euclid's vast dataset will provide the answers, turning theoretical predictions into hard, observational fact. The sheer number of voids it will catalog, from the largest supervoids to previously undetectable mini-voids, will give statisticians an enormous sample to work with, reducing uncertainty and revealing subtle patterns in the architecture of emptiness that we can only guess at today. But one telescope is not working alone. On the ground, the Vera C. Rubin Observatory is preparing for its legacy survey of space and time, a project that will utterly transform our view of the dynamic sky. Night after night for 10 years, its massive mirror will capture the entire visible southern sky, not once but over and over. This is not just a map, it is a movie of the universe. The LSST will detect billions of galaxies, but its true power for void astronomy lies in its ability to measure their motions with incredible precision. It will track the peculiar velocities of galaxies on the edges of voids with a fidelity we have never had before, revealing the subtle gravitational pushes and pulls that shape these empty regions in real time. This kinetic information is like hearing the heartbeat of the void itself. By combining Euclid's deep, three-dimensional map with the LSST dynamic, time-lapse view, we will have a complete picture. We will see the structure of the void and feel its motion simultaneously. This combined data will allow scientists to perform the most rigorous tests of gravity ever conceived, searching for any deviation from Einstein's predictions in the weakest gravitational fields of the cosmos. These observatories are not just tools, they are engines of discovery, built to interrogate the great cosmic nothings and force them to reveal the secrets of dark energy, the nature of gravity, and the ultimate fate of everything we see. These lonely void galaxies are more than just isolated curiosities. They are pristine time capsules, preserving a record of the universe's youth. While most galaxies in the crowded filaments have been transformed by a chaotic history of collisions and interactions, a void galaxy has been left largely undisturbed. Its existence has been one of quiet solitude, allowing it to hold onto the primitive conditions of an earlier cosmic era. We can think of a typical galaxy in a dense cluster as a city that has been constantly rebuilt, its ancient architecture buried under modern skyscrapers. A void galaxy, by contrast, is a remote village that has remained unchanged for centuries, its original structures still intact and telling a clear story of its origins. This makes them invaluable living fossils. Astronomers study them not by looking billions of light years back in time, but by examining our cosmic backyard. By analyzing the light from a void galaxy, we can dissect its life story. We find that they are often rich in primordial hydrogen and helium gas, the raw, unprocessed fuel that filled the universe after the Big Bang. This gas has not been blown away by the violent winds from nearby supernova or stripped by the harsh environment of a galactic cluster. It remains a vast, cool reservoir that has fueled a slow and steady trickle of star formation for billions of years. The stars themselves tell a similar tale. They tend to be poorer in heavy elements, the metals that are forged in stellar cores and scattered by explosions. This lower metallicity is a hallmark of youth in the cosmic sense, a sign that the galaxy has not undergone the rapid, enriching cycles of star birth and death that define more social galaxies. Every aspect of their quiet life, from their rotating gas disks to their peaceful star-forming histories, offers a direct glimpse into how all galaxies behaved in the early universe, before the cosmic web grew into its modern, crowded state. In the profound silence of the void, the distant past is not a faint image, but a living, breathing reality. This same echo of creation resonates within the profound quiet of the voids themselves. The cosmic sound waves that stamped a preferred scale onto the galaxy clusters also left their mark on the emptiness. When scientists analyze the distribution of these voids, they find that the distances between their centers are not random. There is a distinct peak, a subtle statistical preference for voids to be separated by about 500 million light-years. This is the Baryon acoustic oscillation, but seen from a completely new angle, the void BAO. It is the ghostly imprint of that first cosmic thunderclap, not on the mountains of matter, but on the vast valleys between them. This method of measuring the universe's expansion is, in many ways, even more powerful than using galaxies alone. Think of it like trying to measure the dimensions of a room. Using galaxies is like measuring the distance between pieces of furniture that have been shoved into messy piles, their positions distorted by constant movement and collisions. But using voids is like measuring the empty space between those piles. The voids are simpler, more spherical, and far less affected by the messy, non-linear gravitational tugs of war that constantly jostle galaxies within dense clusters. Their pristine geometry offers a cleaner, sharper ruler. By precisely measuring the apparent size of this void BAO scale across different cosmic epochs, cosmologists can chart the expansion history of the universe with phenomenal precision. This independent and refined technique cross-checks all other measurements, tightening the constraints on dark energy and bringing us closer than ever to understanding the true nature of the force that governs our cosmic fate. These vast cosmic bubbles are rarely perfect spheres. Their shapes are warped and sculpted by the immense gravitational tides of the surrounding cosmic web. Picture a soap bubble floating in a complex lattice of wires, its surface subtly distorted by the pull from every direction. This is the reality of a cosmic void. The gravitational pull from a nearby supercluster will stretch the void in one direction, while the countervailing tug from a massive filament will compress it from another. The result is a void that is generally elliptical, a slightly squashed sphere, or even a more complex amoeba-like form. This morphology is not random. It is a direct imprint of the large-scale environment, a fossilized record of the gravitational forces that have been acting upon it for billions of years. By meticulously measuring the average shape and alignment of thousands of voids, cosmologists gain a powerful new tool. The degree of ellipticity and the specific orientation of these voids relative to the filaments of the web are exquisitely sensitive to the properties of dark matter. Different candidates for the dark matter particle, whether it is cold, warm, or something more exotic, would lead to different clustering patterns in the early universe. These initial patterns would then be amplified by gravity, ultimately dictating the strength of the tidal forces that mold the voids. A universe with fast-moving, warm dark matter would produce weaker small-scale structures, leading to rounder, more pristine voids. A universe dominated by slow-moving, cold dark matter would build a more intricate web with stronger filaments, resulting in more significantly distorted and elongated voids. The precise shapes we observe today therefore act as a cosmic fingerprint, allowing us to trace back through time and identify the fundamental nature of the invisible particle that makes up most of the matter in the cosmos. The geometry of nothing, it turns out, holds the key to everything. This missing matter is a ghost that has haunted cosmology for decades. Our most precise calculations, based on the afterglow of the Big Bang, tell us exactly how many protons and neutrons, the ordinary stuff of stars and planets, should exist in the universe. Yet when we add up all the visible matter in every galaxy, star, and cloud of dust, we come up dramatically short. Nearly half of all the ordinary matter in the cosmos is simply unaccounted for, a phantom population of atoms that must be hiding somewhere. This is the missing Baryon problem, and the leading suspect for its hiding place is the very substance that fills the cosmic voids. That whisper-thin, superheated plasma known as the warm-hot intergalactic medium, the WIM, is believed to be the final resting place for these lost atoms. It is the universe's ultimate attic, where the majority of normal matter has been stored away in a form so diffuse our telescopes have struggled to see it. The gas is so hot it should glow in X-rays, but its density is so incredibly low that the signal is millions of times fainter than anything we can currently detect. Finding it is like trying to spot the heat from a single candle on the surface of the moon. So how do we hunt for this cosmic ghost? The next generation of space observatories is being engineered for this very purpose. New X-ray and ultraviolet telescopes will act as the most sensitive fishing nets ever conceived, designed to trawl the great cosmic voids and catch the faint signature of the WIM. They will not look for the gas itself, but for its subtle imprint on the light of distant quasars, the brilliant beacons that shine from the edge of the observable universe. As this powerful light travels through the filamentary walls of the cosmic web and across the vast voids, atoms in the WIM will absorb very specific wavelengths, creating a unique barcode of absorption lines in the quasar's spectrum. Each line is a fingerprint, identifying an element like oxygen or hydrogen and revealing the density and temperature of the gas it passed through. By collecting the light from thousands of quasars, we can build a statistical map of this invisible ocean, proving that the great voids are not empty at all, but are in fact the universe's primary reservoirs of normal matter. Solving this mystery would close one of the biggest chapters in modern cosmology, finally balancing the cosmic books and confirming that what we once called nothing is, in reality, almost everything. The profound quiet of a cosmic void is more than just an absence of stars. It is the universe's ultimate clean room, a sterile environment where the faintest whispers of new physics might finally be heard. In the crowded, brilliant chaos of galaxy clusters, the signals from exotic particles or subtle forces are drowned out by the roar of normal matter. But inside a void, the background noise fades to a near-silent hum. This makes these empty regions perfect for hunting the universe's most elusive ghosts, starting with dark matter itself. We know dark matter's gravitational pull shapes the cosmos, but we have never directly detected the particle responsible. Many theories suggest these particles are not completely stable, that they might occasionally decay, emitting a faint trickle of radiation as they do. In a place teeming with normal matter, that faint signal would be impossible to pick out. But in a void where the fog of atoms is at its thinnest, a single, consistent emission line appearing across the vast emptiness could be the smoking gun we have been searching for. It would be like hearing a single, pure note sustained in an otherwise silent hall. Furthermore, the emptiness provides a unique testbed for the relationship between the universe's two great mysteries, dark matter and dark energy. Are they completely separate entities, or could they interact in some subtle way? In the dense core of a galaxy cluster, dark matter's overwhelming gravitational influence masks any potential push or pull from dark energy. But within a void where dark matter is also sparse, the delicate balance of power shifts. If dark energy is somehow transferring energy to dark matter, or if they are repelling one another, the effect would be most visible in the accelerated growth and specific shapes of these empty regions. A void that expands just a little too fast, or whose walls collapse in an unexpected way, could be the first clue to a conversation happening in the dark sector of the universe, a dialogue we are only now learning how to listen for. These great nothings are not passive. They are active laboratories where the fundamental rules of reality are written in the quietest possible ink. This cosmic foam of emptiness is the universe's true skeleton. We have long described the cosmos as a web of shining galaxies, but this perspective is fundamentally upside down. The filaments and great walls are not the primary structure. They are merely the boundaries where expanding bubbles of nothingness press against one another. Our entire observable universe is a colossal collection of these voids, a foam of breathtaking scale where each bubble is hundreds of millions of light-years wide. The galaxies we so carefully map are incidental, a thin and glittering scum left behind on the surfaces of these colliding spheres of emptiness. Think of the foam in a sink or a vast bubble bath. Your eye is drawn to the shimmering films where the soapy walls meet, tracing out a complex network of intersections. You do not think of the bubbles as gaps in the walls. You understand that the walls exist only because of the bubbles. The cosmic web operates on the very same principle. The voids are not the absence of structure, they are the structure itself. Their relentless, dark energy-driven expansion is what piles matter up at their boundaries, squeezing gas and galaxies into the brilliant filaments we see. Without these great nothings pushing outward, the universe would be a formless, homogeneous haze. Emptiness is the active, constructive force that carved the cosmos into its present form. This inversion of view changes everything. It means that to understand why galaxies are where they are, we must first understand why nothing is where it is. The grand narrative of cosmic evolution is not the story of how matter clumped together, but the story of how emptiness stretched itself apart, defining all of reality in its wake. Even the flow of time itself is warped by these cosmic voids. According to Einstein's theory of general relativity, gravity does not just bend space, it also stretches time. A massive object like a planet or a star creates a deep gravitational well, and at the bottom of that well, time passes more slowly relative to the outside. This is gravitational time dilation. Now consider a cosmic void. It is not a well of gravity, but a hill. The relative lack of mass means the gravitational potential is higher there. And on top of that hill, time ticks just a little bit faster. The difference is incredibly subtle, perhaps gaining only a fraction of a second over billions of years compared to time within a dense galaxy cluster. With our current technology, this effect is entirely immeasurable for individual voids. Yet its theoretical existence is profoundly important. It confirms that a void is not merely a passive backdrop, an empty stage upon which the universe plays out its drama. It is an active participant, a region of spacetime with its own distinct physical properties. The void has a gravitational signature, and it has its own rate of time. This transforms our understanding of emptiness from a simple concept into a real, physical environment within the curved geometry of the cosmos. The great nothing is not nothing at all. It is a place where the very fabric of reality is configured differently. This delicate cosmic architecture is not a random accident, but a prerequisite for our own existence. The sheer scale of the voids and their precise balance with the brilliant filaments of the cosmic web might be the only reason we are here to observe them. This idea is known as the Anthropic Principle. It suggests that the universe we observe must be compatible with the existence of conscious life, because if it were not, we simply would not be here to see it. Consider the primordial seeds from which all structure grew. Those initial quantum ripples had a very specific amplitude. What if they had been stronger? Gravity would have acted with ferocious speed, pulling matter into monstrously dense clusters and leaving only tiny, insignificant voids. The universe would be a tapestry of brilliant, colliding galaxies, a cosmic battlefield where stellar systems are constantly torn apart by intense gravitational tides. In such a dense and violent universe, stable solar systems and peaceful, life-bearing planets would be nearly impossible to form. The environment would be far too chaotic and energetic for the delicate chemistry of life to ever take hold. Now consider the opposite scenario. What if those initial ripples had been much weaker? Gravity would have been a lethargic, ineffective sculptor. Matter would have barely clumped together at all. The cosmos would be dominated by immense, dark voids, so vast and empty that galaxies might never have ignited. The universe would be a cold, thin soup of hydrogen and helium, with no dense knots to forge stars and planets, and no cosmic neighborhoods warm enough to nurture life. Our universe exists in a narrow, golden mean. The initial fluctuations were just right, strong enough to build galaxies and stars, but not so strong that the universe tore itself apart in a frenzy of collisions. This perfect balance created a cosmos with a specific void-to-cluster ratio, a landscape with both fertile islands of matter and the vast, empty spaces between them. Our presence here is a testament to this specific cosmic recipe. We do not live in a random universe, but in one whose fundamental constants and initial conditions allow for the emergence of complexity and consciousness. The great voids are not just distant curiosities, they are a fundamental part of the only kind of universe that could ever have asked about them in the first place. This cosmic feedback loop is the universe's great engine of creation and destruction. Voids do not simply exist beside the filaments of the cosmic web, they actively forge them. As a void expands under the push of dark energy, it behaves like a growing bubble in a pan of cosmic batter. Its outer surface presses relentlessly against the surrounding matter, shoving galaxies and gas clouds together, herding them into the dense, luminous walls and filaments we observe. This process is a continuous, self-reinforcing cycle. The more a void grows, the more effectively it evacuates its center, and the stronger the pressure becomes on its boundaries, further compressing the matter there. That compressed matter then forms even stronger gravitational anchors, which in turn accelerates the void's own expansion. It is a beautiful, paradoxical dance where emptiness and fullness give rise to one another. The great voids are not passive bystanders in the story of the cosmos. They are the primary sculptors, carving out the grand architecture by pushing everything else into place. This dynamic relationship means that the brilliant cities of the cosmic web owe their very existence to the expanding deserts that surround them, but the void's contribution is even more direct. Those thin, superheated tendrils of gas known as the warm-hot intergalactic medium are not stationary. Vast rivers of this primordial material slowly drain from the void regions, flowing along the gravitational gradients toward the hungry filaments. When these gas streams reach the dense environments of the filaments, they can cool, condense, and fall onto the waiting galaxies within. This is a cosmic supply chain where the raw hydrogen fuel for new stars is actively mined from the emptiest regions of space. A galaxy forming new suns in a brilliant filament might be powered, in part, by gas that has traveled for hundreds of millions of years from the heart of a neighboring void. The emptiness is not barren. It is a fertile plain whose resources are constantly being harvested to build the universe's most luminous structures. The same quantum whispers that seeded the cosmic web are frozen within the voids themselves. Every detail of their vast emptiness, from the subtle curve of their boundaries to the precise distances between them, is a direct message from the universe's first split second. This epoch, known as cosmic inflation, was a period of exponential expansion far more violent than anything happening today. In that fleeting moment, smaller than a trillionth of a second, the entire observable universe was blown up from a quantum speck, and the microscopic ripples that would one day become everything were imprinted upon its fabric. The specific character of those ripples, their strength and their pattern, was set by the physics of inflation itself. Different theoretical models for what powered this incredible expansion predict different statistical blueprints for the infant cosmos. Some models would have created a universe dominated by many small voids. Others would have seeded fewer but far more colossal, empty regions. The precise distribution of void sizes, their shapes, and how they themselves cluster together in space is a fossilized record of that primordial physics. When our most powerful telescopes, like Euclid, deliver their ultimate catalog of millions of voids, they are not just mapping emptiness. They are providing a massive dataset that cosmologists can compare against the predictions of countless inflationary theories. It is a process of elimination on a cosmic scale. Does the observed population of voids, from the tiny mini-voids to the staggering supervoids, match what a particular model of inflation forecasts? If the statistical properties align, that model survives. If they clash, the model is ruled out. In this way, the great voids become our most powerful time machine, allowing us to peer back past the formation of the first stars, past the release of the cosmic microwave background, and directly test our ideas about the universe's very first moment of creation. The silent, expanding nothingness that defines our cosmic present is in fact the clearest echo we have of the first something. The profound silence of a cosmic void is a grand deception. At the most fundamental level, what we call emptiness is a state of pure, frenetic activity. Empty space, according to quantum field theory, is not a still and passive stage. It is the lowest energy state of a field, a dynamic medium seething with potential. This quantum vacuum is a turbulent foam where virtual particle pairs spontaneously blink into existence, borrowing energy from the universe for an impossibly brief moment before annihilating each other and vanishing back into the void. This is not a theoretical abstraction. It is a verified phenomenon with real-world effects. In the emptiness between stars, this constant creation and destruction exerts a tiny, measurable force, a pressure that can subtly influence the motion of objects and even shift the energy levels of atoms. The cosmic void, on its grandest scale, is the ultimate expression of this quantum restlessness. It is the quantum vacuum writ large, a domain where the ephemeral dance of virtual particles is the primary reality. This leads to one of the most profound connections in all of physics. The energy inherent to this quantum vacuum, the energy of empty space itself, is a prime candidate for the source of dark energy and the cosmological constant in Einstein's equations. The same vacuum energy that causes particles to flicker in a lab might be the very force inflating the universe on a cosmic scale. Yet a colossal problem remains when physicists calculate the predicted strength of this vacuum energy based on quantum theory. The result is a number staggeringly larger than the observed value of dark energy, off by a factor of 1 followed by 120 zeros. This is the worst prediction in the history of science, a glaring disconnect between our understanding of the very small and the very large. It suggests that either our grasp of the quantum world is deeply incomplete, or that some unknown mechanism is cancelling out almost all of this vacuum energy, leaving behind only the faint, repulsive whisper we call dark energy. The great cosmic voids, in their serene and immense emptiness, are not just holes in the cosmos. They are the largest possible laboratories for testing this fundamental link, forcing us to confront the possibility that the true nature of reality is written not in the stars, but in the seething, hidden energy of nothing itself. This profound emptiness we find written across the cosmos is not a new idea to humanity. Our own history of art, music, and philosophy is a long meditation on the very same theme. For centuries, human creativity has understood that meaning is often defined by what is absent. In Japanese ink wash paintings known as ma, the empty space is not a passive background. It is an active element, a silent participant that gives form and weight to the single, stark brushstroke. Without that emptiness, the stroke would be just a mark, but surrounded by void, it becomes a mountain, a vast horizon, or a solitary figure in an immense landscape. The emptiness gives the object its context and its power. The same principle resonates in the silent pauses between musical notes. A composer like Beethoven did not just write sounds, he choreographed silence, using its tension to make the following chord feel triumphant or tragic. That rest, that moment of pure nothing, is what makes the music breathe and gives its return such emotional force. This cultural intuition extends into the very heart of philosophy. The concept of the void, of sunyata in Buddhist thought, is not a nihilistic nothingness but a fertile emptiness, a ground of potential from which all forms and phenomena arise. It is the understanding that things exist only in relation to their absence, that form and emptiness are two sides of the same reality. The cosmic void is the ultimate physical manifestation of this ancient wisdom. It is the universe itself engaging in the practice of Ma, using vast, silent expanses to define the brilliant, glittering structures of the cosmic web. These great nothings are not just astronomical phenomena, they are a cultural and psychological mirror. They reflect back at us a truth we have always sensed but are only now proving on a galactic scale, that the background is not merely a backdrop. It is the foundational substance from which all foreground emerges. Our scientific discovery of the cosmic void is, in a deep sense, a rediscovery of a timeless human insight, scaled up to encompass the entirety of existence. At the heart of the deepest cosmic void, the night sky would be a permanent monument to solitude. If you stood on a planet orbiting the lone star of a void galaxy, you would look up into an almost perfect blackness. The familiar, hazy band of our Milky Way would be your entire universe, a single, swirling ribbon of starlight in an endless sea of nothing. No other galaxies would be visible to your naked eye. The Andromeda Galaxy, a faint smudge in our own sky, would be absent. The brilliant pinpricks of nearby galactic neighbors would simply not exist. Your celestial map would be nearly blank, a star chart defined by its absences. This is the ultimate desert, a domain of such profound isolation that the very concept of a cosmic community becomes meaningless. The darkness between the stars here is not a temporary curtain that rises to reveal other islands of light, but a permanent, fundamental reality. You are not in a quiet neighborhood, you are adrift in the cosmic equivalent of the open ocean, so far from any shore that the very idea of land becomes a myth. This environment is the most extreme the universe has to offer, a polar opposite to the brilliant, chaotic metropolises of galaxy clusters. It forces us to recognize that the cosmos contains realms of existence so different from our own that they challenge our very definition of what a universe should be. These vast cosmic nothings are far more than just empty space. They are dynamic, evolving entities that have fundamentally reshaped our understanding of the cosmos. We have seen that they are not passive holes, but active laboratories where we can probe the nature of dark energy, watching it inflate these regions faster than the universe itself. They serve as rigorous testing grounds for gravity itself, placing Einstein's theories under unprecedented strain in the weakest gravitational fields. These voids are the universe's ultimate attics, hiding the majority of its normal matter in a whisper-thin, superheated mist that we are only now learning to detect. And they are pristine fossils, preserving the echo of the universe's first sound and the quantum ripples from its violent birth. The sheer, unimaginable scale of these voids forces a profound philosophical shift. They challenge our most basic categories of something and nothing, revealing that emptiness is not a passive backdrop. It is an active, informative, and constructive component of reality. The great voids have taught us that to truly comprehend the cosmos, we must study its silences as intently as its songs. Our journey through the cosmic voids reveals a universe defined not by its shining landmarks, but by its profound silences. These vast expanses of nothingness are paradoxically brimming with consequence. They are not mere empty holes in the cosmic fabric, but fundamental features that actively sculpt the cosmos. They drive its accelerating expansion and hold the master keys to its deepest physical secrets. From placing Einstein's theory of gravity under the most extreme strain to illuminating the true nature of dark energy, these great nothings have fundamentally revolutionized our understanding of reality itself. Every new void we map is another piece of the grand puzzle, another clue in our quest to comprehend the forces that govern everything from the quantum foam to the cosmic horizon. As our telescopes peer ever deeper into these dark expanses, we edge closer to answering humanity's oldest and most profound questions about where we came from and where the universe is ultimately headed. So the next time you gaze up at a clear, dark sky, remember to ponder not just the brilliant points of light, but the immense, silent voids between them. For in that profound emptiness, the cosmos speaks its most enduring truths.